Hey guys, tonight we are going on a journey. A very, very long journey. Close your eyes for a moment and picture this. We're standing on a cold, desolate rock, spinning through the infinite blackness. There's no air to breathe, no sun to warm us, just the distant glow of a young star and the silent, swirling chaos of space. In fact, if you were actually here at this point in our story, you'd probably be vaporized in a millisecond. But that's a small detail. What we're witnessing is a grand cosmic ballet, the very beginning of a world. Before you get too comfortable and drift off, please take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, I'm curious, where in the world are you right now? What time is it for you? Let me know in the comments below and let's get lost in this story together. Before our story even begins, there is only a vast empty canvas of cosmic dust and gas. You could think of it as a great silent cloud, stretching for light years through the void. This is our raw material, the fundamental building blocks of everything we know. Imagine this cloud as a great cosmic kitchen, filled with the scattered leftovers of dead stars, carbon, oxygen, iron, all the heavy elements that were forged in the fiery hearts of ancient suns. For eons, this cloud just drifted, a quiet nebula of potential, a cosmic whisper waiting to be heard. But then, a whisper becomes a hum. Somewhere nearby, an old star, a real giant, one that lived and died long before our own sun was born, finally collapses. Its death is violent, a supernova, and this great explosion sends a shockwave rippling through the tapestry of space. When this wave reaches our cloud, it's like a gentle finger poking a sleeping giant. The dust and gas, once so evenly dispersed, begin to feel the pull of their own gravity. They start to condense, to swirl, to form small pockets of density. And as they get denser, they start to attract more material, and the process accelerates. It's a slow, quiet domino effect, but the stakes are unimaginably high. At the center of this swirling disk, a new star is born, our sun. It ignites with a flash, and its solar wind, a steady stream of charged particles, begins to clear out the inner part of the disk, pushing away the lighter gases. But in the outer reaches, the solid bits, the grains of cosmic sand and rock, start to collide. They stick together, forming larger and larger clumps. It's like a cosmic snowball fight, except instead of snow, you're throwing dust bunnies and pebbles, and they're growing into rocks the size of houses. And those houses are colliding and growing into mountains. This process, known as accretion, is the fundamental mechanism by which planets form. It's a slow, patient, and incredibly messy dance. For millions of years, our young solar system is a shooting gallery, a chaotic junkyard of protoplanets and asteroids smashing into each other. But there's a certain logic to the madness. The larger a clump becomes, the stronger its gravitational pull, and the more material it attracts. Soon, a few dominant players emerge from the chaos, clearing out their orbital paths and growing into the planets we recognize today. The one that concerns us is the one we're standing on. In the earliest days of its formation, the Earth was nothing more than a ball of molten rock, a fiery hellscape of constant bombardment. It was a place of unimaginable violence, and yet it was also a place of immense promise. Every asteroid, every cometary ice ball that slammed into it, was adding a new layer to its story, a new piece to its puzzle. The heat was so intense that any water would have instantly vaporized, turning the air into a thick, steamy fog, a perpetual hot shower from which there was no escape. One of the fascinating and still debated questions about this period is the origin of the moon. The prevailing theory, known as the giant impact hypothesis, suggests that a Mars-sized celestial body named Theia collided with the proto-Earth. This wasn't a glancing blow. It was a catastrophic smash-up that vaporized both planets' mantles and sent a massive ring of debris into orbit around the Earth. Over time, this ring of debris coalesced, forming our moon. It's a story of creation born from destruction, a cosmic birth that left our young planet with a steady, stabilizing companion. It also raises a question. Would life as we know it have ever emerged without the moon's gravitational influence to stabilize our planet's axis and create the tides that would later be so crucial to early life? We don't really know, but it's a beautiful thought. The physics behind this, the immense forces, the specific angles of impact, the sheer scales involved, are almost incomprehensible to us. We try to grasp them with our minds, to model them with our computers, but it's like trying to understand an ocean by holding a single drop of water. The reality is grander, more complex, and more mysterious than we can possibly imagine. The universe is a place of such profound and elegant violence, where planets are born from destruction and life is forged in the aftermath of fire. The early Earth, with its fiery core and relentless rain of asteroids, was a canvas in flux. It was a world in a state of becoming, not being. It had no oceans, no atmosphere as we know it, just a swirling cloud of superheated steam and a surface glowing with a quiet, persistent heat. This was the opening act, the prologue to a story that would take billions of years to unfold. And for a long, long time, nothing happened. Not in a way that we could easily observe. The planet was simply cooling. Think of our planet at this stage as a giant cosmic kiln. Inside, the heaviest elements like iron and nickel, drawn by gravity, began to sink toward the center, forming a dense, liquid metallic core. Lighter silicate materials floated to the surface, creating a thin, fragile crust. This process, called planetary differentiation, is what gives Earth its distinct layers: the core, the mantle, and the crust. It's a slow, steady sorting of materials, a cosmic sifting that sets the stage for everything that follows. We can think of the Earth's core as a kind of beating heart, a furnace of immense pressure and heat that drives so much of what we will later see on the surface. We can't see it, of course, and we can't touch it, but we know it's there, a hidden engine humming away beneath our feet. Now, imagine an odd scientific paradox. There's a theory in planetary science about the faint young sun paradox. It posits that during this early period, our sun was about 30% dimmer than it is today. And yet, geological evidence suggests that the Earth was not a frozen, lifeless ice ball, but rather had liquid water. How is this possible? The likely answer is a thick, primordial atmosphere, perhaps rich in greenhouse gases like methane and carbon dioxide, which trapped the sun's warmth and kept the planet from freezing over. This is a subtle, yet profound mystery, a reminder that the story of our planet is full of hidden variables, of cosmic coincidences that had to be just right for our story to even begin. This chaotic, molten world was a harsh but fertile ground. The collisions were bringing not just rock, but also water ice and other volatile compounds to the surface. And as the planet slowly, incrementally, began to cool, that thick, steamy atmosphere would eventually condense, leading to a downpour of biblical proportions. A rain that lasted for centuries, even millennia, creating the first great oceans. This was the moment the Earth truly became a canvas for life, a world of both fire and water. But for now, we are still in the fiery stage, watching as the primordial dust settles and the planet finds its balance. It's a quiet time, a time of slow, patient transformation, and a testament to the fact that even the most chaotic beginnings can lead to a state of profound and beautiful order. The rain began quietly, almost as a whisper. It was not the gentle pitter-patter we know today. but something far more immense and sustained. Imagine a global thunderstorm that rages for thousands of years, a continuous deluge that slowly, patiently cools the glowing surface of the earth. The air was thick with vapor and steam, an opaque blanket that shielded the ground from the faint sunlight. The sound, if there had been anyone to hear it, would have been a deafening roar. The sound of a world being born anew, washed clean of its fiery past. As the torrent continued, the vast, superheated atmosphere began to give way. The steam condensed and fell back to the surface, and with each drop, a tiny bit of the planet's tremendous heat was radiated away into space. This was a process that unfolded over eons. But in the slow geologic time of our young world, it was the main event. It was the Earth taking its first proper bath, shedding its primordial skin of fire, and unveiling the true canvas for life. Beneath the endless rain, something incredible was happening. The molten rock, the newly formed crust, was finally solidifying. It was still hot, still prone to fracturing and shifting, but it was a solid foundation. And into the low-lying basins and deep valleys of this new landscape, the water collected, forming the first oceans. These were not the calm blue seas we know. They were dark, murky, and hot, filled with dissolved minerals from the surrounding rocks. And they were immense, covering the entire planet in a single great watery expanse. These early oceans were the planet's first great innovation. They were a stable, protective environment, a womb in which the first stirrings of life could take hold. The water acted as a solvent, a medium in which chemicals could mix and react in a way that was impossible in the harsh, dry environment of space. It was a chemical soup, and the ingredients were all there, a strange cocktail of carbon, hydrogen, nitrogen, and all the other elements that had been swirling through the cosmos for billions of years. But something was still missing. The spark. The journey from non-life to life is one of the greatest mysteries in all of science, a process known as abiogenesis. It's the question of how a collection of inert molecules can suddenly begin to replicate, to metabolize, to become something more than the sum of its parts. And while we have many theories, the truth is, we don't really know for sure. Some scientists speculate that life began in the deep-sea hydrothermal vents, where superheated mineral-rich water spews from cracks in the ocean floor. The energy from these vents could have provided the fuel for the first chemical reactions, and the protective, contained environment could have allowed the fragile first molecules to form. It's a beautiful thought, a kind of dark and secret garden at the bottom of the world, where life began in the total absence of sunlight. This is one of the more romantic notions in science, the idea that something so complex and beautiful could arise from a seemingly random series of chemical reactions. And while we have created simple self-replicating molecules in a lab, we have yet to recreate the full breathtaking complexity of a living cell. It's a reminder that even when we think we're close to a solution, the universe still holds its secrets tightly. As we ponder this profound mystery, it's worth considering a lesser-known scientific truth about our own planet. The Earth's interior is a dynamic, living system. The heat that drives the geothermal vents and powers our continent's movements is a remnant of the planet's formation. But there's a fascinating, and often overlooked, contributor to this internal heat: radioactive decay. Elements like uranium, thorium, and potassium in the Earth's mantle and crust are constantly breaking down, releasing a steady stream of energy. It's a quiet, invisible furnace that keeps the mantle pliable and fuels the slow dance of our tectonic plates. This process is so slow and so subtle that we rarely think about it, but it's a fundamental part of what makes our planet a living, breathing entity. It's a quiet, consistent hum beneath our feet, a source of energy that has been warming the Earth for billions of years. The first life forms were single-celled organisms, simple and microscopic. They were not impressive in the way that we think of life today, but they were the beginning. The first stirrings of a new kind of existence, one defined by the struggle to survive and replicate. They were pioneers in a brand new world, the quiet heroes of our story. We will never know their names or what they looked like, but every one of us, every tree, every animal, every whisper of a thought can trace its lineage back to them. They were the first, the very first, to solve the great puzzle of existence. They figured out how to use the chemical energy around them, how to repair themselves, how to make a copy. And in doing so, they changed the world forever. Their story is one of patience and adaptation. For billions of years, life on Earth remained microscopic, confined to the oceans. It was an age of slow, patient experimentation, of tiny cells bumping into each other, exchanging genetic material, and evolving into countless new forms. The Earth itself was still in its infancy, but the stage was set for the next great act. The rain had stopped, the oceans had formed, and a strange new kind of magic was beginning to unfold in the deep, dark waters. And the most interesting paradox of all? The life that would one day take over the world was at this moment an anoxic world, a world without oxygen, for the most potent poison to these early life forms was what we now need to live. The great single ocean was the cradle of a new kind of existence, but it was also a place of quiet, simmering revolution. The first life was simple, a kind of elegant chemical machine that lived by consuming the organic molecules that were so abundant in the primordial soup. But this was a limited way of life. The food supply was finite, a dwindling resource that would eventually run out. Something had to change. A new way of survival had to be invented. And so it was. Deep in the murky, sunless waters, something truly groundbreaking occurred. A tiny single-celled organism, a kind of microbe, developed a new trick. It learned to capture the energy from the sun, to use it to split water molecules, and to turn carbon dioxide into food. It was a process we now call photosynthesis. This was not just a new way to eat. It was a way to create energy out of almost nothing, to turn the sun's light into life. It was a mastery of cosmic energy, a quiet revolution happening on a microscopic scale. But this new trick had a side effect, a byproduct that would have immense and unforeseen consequences. When these early photosynthetic organisms, the cyanobacteria, split water molecules, they released oxygen as a waste product. For the anaerobic life that had dominated the Earth for 1 billion years, this was a poison, a toxic, corrosive gas that was lethal to most of the life forms that existed at the time. This was the beginning of the Great Oxygenation Event. Imagine a slow, silent, and entirely invisible environmental catastrophe on a global scale. For hundreds of millions of years, the oxygen levels in the atmosphere and oceans slowly, inexorably rose. The iron dissolved in the oceans began to rust, falling to the seabed in great layers of red sediment that we now mine as iron ore. The methane and other greenhouse gases that had kept the Earth warm were oxidized, leading to a period of global cooling and possibly the first great glaciation event known as Snowball Earth. This was a world in crisis, a biosphere struggling to adapt to the very thing that would one day make it so vibrant and full of life. It's a profound thought. The very air we breathe, the gas that gives us life, was once a planet-wide toxin. This period also raises an interesting scientific riddle. We can see the geological evidence of this oxygenation in the banded iron formations around the world. But for a long time, the oxygen levels seemed to stabilize at a low level before suddenly skyrocketing. This is known as the boring billion, a long stretch of time where life seemed to hit a plateau. Why did this happen? One idea is that the Earth's mantle, the great layer of rock beneath the crust was still more oxidized than it is today. In this theory, the mantle was a great oxygen sink, soaking up the newly produced gas and preventing it from building up in the atmosphere. This is a subtle and beautiful idea, the notion that the very insides of our planet were involved in regulating the atmosphere, creating a kind of slow planetary scale breathing. The Great Oxygenation Event was a turning point, a filter that only the most adaptable life could pass through. Some organisms went extinct, unable to cope with the new toxic environment, but others, the ancestors of all complex life, found a way. They developed new metabolic processes to not only tolerate oxygen, but to use it to generate far more energy than their anaerobic ancestors ever could. This was the invention of cellular respiration, the ability to burn food with oxygen. It was a metabolic superpower, and it set the stage for the next great act in the story of life. The world was changing. The oceans were filling with oxygen, and a new kind of organism was emerging, one with a more complex cell structure. These were the eukaryotes, and they had a secret weapon. They had engulfed or partnered with bacteria that could perform cellular respiration. This is the endosymbiotic theory, and it's a powerful and poetic idea. The mitochondria in our cells, the little power plants that fuel us, were once free-living bacteria that decided to form a partnership with a larger host cell. It's a story of collaboration, of two different life forms coming together to create something stronger and more complex than either could have been alone. It's a little-known but crucial fact of our existence, a reminder that deep down, we are all made of partnerships, of alliances forged billions of years ago. As we end this part of our journey, let us reflect on the quiet strength of that first microscopic life. They endured a planet of fire, survived a global poisoning, and invented the very air we breathe. They are the silent architects of our world, the forgotten pioneers of a new way of being. And their story is a testament to the fact that even the smallest and most unassuming things can have the most profound impact, reshaping not just the course of life, but the very chemistry of a planet. They remind us that true power is not always loud and violent, but can be as quiet and persistent as a drop of water, or the slow, steady hum of a tiny cell, creating a gas that would one day become the very breath of a world. For billions of years, life on Earth remained a story of the small. It was a microscopic drama playing out in the dark, warm waters of the ocean, a quiet, cellular ballet of division and adaptation. But as the planet's atmosphere became richer in oxygen and the energy from the sun became more readily available, the stage was set for a new kind of performance. The simple, elegant eukaryotes, with their newly acquired power plants, the mitochondria, were ready for something more. The next great leap was the invention of multicellularity. Imagine a group of single-celled organisms, perhaps floating together in a colony, deciding to stop being individuals and start working as a team. This was not a conscious decision, of course, but a slow, gradual process of cooperation. Some cells specialized, becoming the first rudimentary tissues, some for feeding, some for moving, others for reproduction. It was the birth of the organism as we know it, a single coordinated being made up of a complex society of cells. This was a profound shift. A single cell can only get so big, only do so much, but a community of cells working together could grow to immense size and complexity. It's a beautiful thought, the notion that the grand, intricate life forms we see all around us, from the smallest flower to the largest whale, are all just a vast, coordinated team of microscopic laborers. It also raises a philosophical question. At what point does a collection of cells become an individual? A mystery that even today in the fields of biology and philosophy, we don't have a clear answer to. This era of life, often referred to as the Ediacaran period, was a time of strange and beautiful creatures. We only know them from their fossilized imprints in ancient rocks. They were soft-bodied, often looking like quilted mattresses, fronds, or discs. They were unlike anything alive today, a kind of biological experiment that the planet ran for a few 100 million years before moving on to the next act. They lived in a world without predators, a kind of peaceful underwater garden where there was little need for defense or speed. But the peace was not to last. As we move closer to the present, a remarkable event occurred around 541 million years ago, the Cambrian explosion. It was a geological blink of an eye, a period of only about 20 million years. But in that short time, life exploded into a dizzying array of forms. Suddenly, creatures with hard shells, sharp teeth, and complex eyes appeared in the fossil record. It was the birth of the first true animals. Think of it this way. For billions of years, the world was a black and white movie, a quiet, slow-moving story of tiny blobs. And then, in a flash, it became a technicolor action film, filled with hunters and prey, with strange and fantastical beings with legs, claws, and jaws. It was a time of immense evolutionary innovation. This is also when we find the first evidence of a brain, a central processing unit for all the new sensory information that these complex creatures were gathering. This brain, in its earliest form, was just a small knot of nerves, but it was the beginning of consciousness, of thought, and of the incredible complexity that would one day lead to us. One of the fascinating and lesser-known scientific tidbits about this era is the Burgess Shale. This is a fossil bed in the Canadian Rockies that preserved an extraordinary snapshot of Cambrian life. The conditions there were so perfect that even the soft-bodied creatures, the ones that rarely fossilize, were preserved in exquisite detail. When scientists discovered it, they were astounded. They found creatures that looked like they belonged in an alien world, like Anomalocaris, a giant, for its time, predator with a circular mouth and strange, spiked arms. The Burgess Shale is like a hidden library, a record of a world that existed for only a brief moment, but which gave rise to all the animal life that followed. The Cambrian explosion is still a great mystery. What triggered it? Was it the rise of oxygen to a critical threshold? Was it a change in ocean chemistry? Or was it an internal evolutionary push, a kind of snowball effect, where one small innovation, like the invention of a hard shell, sparked 1,000 others? The truth is, we don't really know, but it's a beautiful reminder that our understanding of life's history is still full of gaps, of moments of creation that seemed to defy simple explanation. The world had changed forever. The peaceful, quiet garden of the Ediacaran was gone, replaced by a dynamic, competitive ecosystem. And with the appearance of complex mobile life, the stage was set for the next great migration. For while the ocean was a wonderful place, the land above was still an empty, barren rock, waiting for a new kind of pioneer. The story of life was about to take its first tentative steps out of the water and onto the quiet, desolate land. The world had its first animals, a dazzling menagerie of hard-shelled hunters and their prey, but they were still trapped in a liquid world. The land above the water remained a silent, desolate expanse, a world of naked rock, wind, and the relentless sun. For hundreds of millions of years, the continents had been on a slow, grinding journey, a quiet dance across the planet's surface. This is the great saga of plate tectonics, the fundamental engine that sculpts our world. Imagine the Earth's surface as a great cracked shell. These cracks divide the crust into vast, rigid pieces, or tectonic plates, and these plates are not static. They are in constant slow motion, floating on the semi-fluid layer of the upper mantle below. It's a movement so gradual that over the course of a human life, it's entirely imperceptible. But over the span of millions of years, it can reshape the face of the planet, opening and closing oceans, lifting mountain ranges, and moving entire continents from pole to equator. This grand geologic ballet is powered by the Earth's internal heat, the same heat we talked about in a previous part of our story, the heat from radioactive decay and the remnants of our planet's fiery birth. It's like a great slow-motion conveyor belt, with hot material rising from the core and cooler material sinking back down. This convection drives the plates, causing them to collide, pull apart, and slide past one another. When plates collide, one might be forced beneath the other in a process called subduction. This can create deep ocean trenches and fiery volcanoes. When plates pull apart, molten rock from the mantle rises to the surface, creating new crust and vast mid-ocean ridges. And when they grind past each other, we get the sudden, violent shuddering of earthquakes. It is a slow, methodical process that has, over the billions of years of our planet's history, sculpted the very ground beneath our feet. This constant reshuffling of the continents had a profound impact on the story of life. When continents are all clustered together in a single landmass, a supercontinent, the amount of coastline is reduced and the climate is more extreme. When they are separated, as they are today, the amount of coastline increases dramatically, creating new diverse habitats and influencing ocean currents and global weather patterns. This changing geography acted as a kind of a stage director for life, creating new opportunities and challenges, pushing organisms to adapt or go extinct. We have a fascinating, little-known scientific tidbit related to this: the Wilson cycle. This is the theory that oceans and supercontinents are not just static features, but are on a continuous cycle of opening and closing. An ocean opens as a continent splits apart, widens for millions of years, and then slowly begins to close as the plates reverse direction and collide once more, forming a new supercontinent. This cycle takes about 500 million years to complete, and it means that the map of our world is never truly finished, but is in a state of perpetual slow-motion change. It's a beautiful thought. The idea that the oceans themselves are just temporary features, destined to close up and vanish in the distant future. With the continents finally shifting and settling into something resembling stability, the stage was set for life's next great move. For the first time, a brave group of organisms, the plants, began to colonize the barren land. This was a slow, arduous process. To survive on land, they had to solve a series of new problems: how to get water without being constantly submerged in it, how to support their own weight against the pull of gravity, and how to protect themselves from the sun's harsh UV rays. They invented roots, stems, and leaves, and in doing so, they created the first soil, slowly but surely transforming the naked rock into a fertile ground. This move onto land by plants created an entirely new ecosystem, and it paved the way for the animals to follow. They came out of the water in a series of careful, tentative steps, first as small arthropods, then amphibians, and eventually the first reptiles. But their journey was only possible because the plants had gone first, creating a safe, hospitable environment, a green carpet on which they could walk. The story of life on Earth is, in many ways, a story of movement, from the deep sea to the shallows, from the water to the land. But this story of movement is also a story of connection. The continents, though they move apart, are still linked by the slow, inexorable hum of the planet's interior. And the life on them, though it has diversified into a breathtaking array of forms, is still connected by a single, shared history. The journey was slow, but it was leading to something grand, something that would one day walk upright and wonder at the quiet dance of the continents beneath its feet. With the continents set in their slow, patient dance, and the land now covered in a green mantle of plants, the stage was set for an extraordinary new chapter in life's story. The era that followed, stretching from about 252 million to 66 million years ago, is known as the Mesozoic era. It was a time of immense warmth, with no polar ice caps, And it was a time when the great reptiles rose to dominance. It was the age of the dinosaurs. For millions of years, these magnificent creatures walked the earth, from the nimble feathered hunters to the colossal long-necked herbivores that shook the ground with every step. They came in all shapes and sizes, a dizzying array of biological innovation, and they filled every available ecological niche. The skies were home to the winged pterosaurs, the seas to the great marine reptiles, and the land to the undisputed kings of their time. They were the masters of their domain, a testament to the power of adaptation and the incredible diversity that evolution can produce. The Mesozoic was a different world. The air was richer in carbon dioxide than it is today, and the climate was more uniform across the globe. Vast, shallow seas covered large parts of the continents, creating perfect conditions for the proliferation of marine life. And on land, the forests were not made of the flowering trees we know, but of towering ferns and gymnosperms like cycads and conifers. It was a lush, green and humid world, a perfect Eden for the cold-blooded giants that roamed it. This era also saw the quiet, humble rise of the first mammals. They were small nocturnal creatures, living in the shadows of the dinosaurs, scuttling through the undergrowth in search of insects. They were not impressive, but they had a secret weapon. They were warm-blooded. This allowed them to be active at night and in cooler temperatures, giving them an evolutionary edge that would one day prove to be crucial. Think of them as the quiet, patient observers, waiting in the wings for their turn on the main stage. One of the most mind-bending scientific concepts related to this period is the geologic timescale. We talk about millions of years so easily, but it's a scale that is almost impossible for our human minds to grasp. When you say the dinosaurs ruled for 150 million years, it's a number that just floats in the air. To put that into perspective, the time that separates us from the last T-Rex is roughly the same amount of time that separates the T-Rex from the first feathered dinosaurs. It's a vast, empty stretch of time, a quiet chasm where continents drifted and life slowly evolved. It's a reminder that we are just a tiny, fleeting moment in the grand sweep of planetary history. This era also holds a profound and little-known truth about the relationship between plants and animals. The dinosaurs and other land animals were dependent on the plant life for their sustenance, just as they are today. But the plants themselves were also evolving and adapting to the world around them. For example, some plants developed new defense mechanisms, like thorns or bitter chemicals, to protect themselves from the hungry herbivores. In a way, it was a kind of an arms race between the plants and the animals, a constant process of one evolving to overcome the other. This dynamic relationship is a quiet, continuous story that is still playing out all around us today. But the Age of Giants, for all its splendor and majesty, was not destined to last. Remember the asteroid bombardment from the beginning of our story? The universe was about to remind our planet that its journey was still subject to cosmic forces. And the great silent dance of the planets and stars was about to send one last, great messenger to our world. The world was at the peak of its glory, but it was standing on the edge of a great precipice, a change that would wipe the slate clean and start the story of life all over again. We don't know for sure, but there's a fascinating scientific question about whether this was a singular event. Did the dinosaurs' demise happen in one instant, or were they already in decline? There is some evidence to suggest that sea levels were changing and that volcanic activity was on the rise before the asteroid impact. This raises the question of whether the impact was the final nail in the coffin, or if the dinosaurs would have disappeared anyway. This is a subtle but profound mystery, and a reminder that even in the most certain moments of our planet's history, there is always more to learn, more to wonder at, and more to be humbled by. The age of the dinosaurs came to a sudden, dramatic end. Imagine the world on a normal day about 66 million years ago. The skies were clear, the great herbivores were grazing, and the smaller predators were hunting. But then, a quiet whisper in the cosmic void became a fiery roar. A giant asteroid, somewhere between 10 and 15 kilometers wide, hurtled through the atmosphere. It was a silent messenger from space, a final reminder of our planet's cosmic heritage, and it was about to change everything. The impact was unimaginably powerful. It struck the Earth near what is now the Yucatan Peninsula in Mexico, creating a crater over 180 kilometers in diameter. The force of the impact was more than 1 billion times stronger than the atomic bomb dropped on Hiroshima. It was an instantaneous, cataclysmic event that sent a shockwave around the globe, triggered massive earthquakes and volcanic eruptions, and threw a colossal cloud of pulverized rock, soot, and steam into the atmosphere. The immediate aftermath was pure chaos. An enormous tsunami, a wall of water hundreds of meters high, raced across the Gulf of Mexico and crashed onto the surrounding coastlines. A fiery blast, a pulse of superheated air, radiated out from the impact site, incinerating everything in its path. And then came the slow, creeping darkness. The dust and soot in the atmosphere blocked out the sun, plunging the entire planet into a period of prolonged darkness and cold. This is known as impact winter. The lack of sunlight meant that plants could no longer photosynthesize. The great forests withered and died, and with them, the herbivores that fed on them. The ecosystem, which had been so vibrant and complex, collapsed from the bottom up. The dinosaurs, magnificent and powerful as they were, simply couldn't find enough to eat. It was a slow, agonizing process, a kind of planetary famine that brought an end to an entire way of life. This is a powerful illustration of the delicate balance of an ecosystem. The loss of a single, seemingly minor element, the sun's light, set off a chain reaction that brought down the mightiest creatures that had ever walked the earth. It's a humbling reminder that even the most dominant life forms are dependent on the most fundamental of resources, and it is also a testament to the random, chaotic forces of the universe. The dinosaurs didn't die because they were weak or because they were not well suited to their environment. They died because of an unlucky cosmic accident. One of the interesting and somewhat grim scientific facts about this period is the IR-192 isotope layer that can be found around the world. Iridium is an element that is extremely rare in the Earth's crust, but is very common in asteroids and other extraterrestrial objects. When scientists started finding a thin layer of this element in geological strata that corresponded to the end of the Cretaceous period, they knew they were onto something. It was a cosmic fingerprint, a smoking gun left behind by the very object that had ended the dinosaurs' reign. It was a silent, scientific clue left in the rock record for us to find, a reminder that the universe had a hand in shaping our destiny. The end of the dinosaurs was a beginning for something else. With the great reptiles gone, a vast new set of ecological niches opened up. The world, once a kingdom for giants, was now a land of opportunity. The small, quiet mammals that had been living in the shadows, waiting for their chance, now had their moment. They were not strong, they were not particularly fast, but they had a crucial advantage. They were adaptable, and they were about to inherit the Earth. This raises a fascinating question about the nature of survival. Is it strength and size that guarantee success? Or is it quiet persistence and adaptability? The story of the dinosaurs and the mammals is a powerful argument for the latter. The meek, in a cosmic sense, had inherited the Earth. Their rise was not a violent, sudden affair, but a slow, patient climb to the top, a testament to the power of simply enduring. The stage was now set for the rise of a new kind of life, a life that would one day build cities and tell stories about the fiery end of the great reptiles. The cosmic winter that followed the Great Impact was a time of immense hardship and loss, but it was also a time of quiet opportunity. With the dinosaurs gone, The world was no longer dominated by giants. The playing field had been leveled, and the small, unassuming mammals that had lived in the shadows for over 100 million years finally had their chance to shine. This period, the Cenozoic era, is often called the Age of Mammals. In the absence of their great reptilian competitors, mammals diversified at an astonishing rate. They evolved to fill every ecological niche, from the burrowing moles to the soaring bats, from the great whales that returned to the sea to the primates that would one day climb down from the trees. It was a rapid, explosive period of evolution, a testament to the power of a single change in the environment to open up a whole new world of possibilities. The climate of the Cenozoic was dynamic and ever-changing. The continents continued their slow drift, and as they did, they shaped new ocean currents and weather patterns. The world went from a warm, tropical planet to one with cooler poles, and, eventually, a series of great ice ages. This constant environmental pressure pushed mammals to adapt, to develop new traits to survive in a world that was always in flux. One of the fascinating and often overlooked aspects of mammalian evolution is the development of a unique reproductive strategy. Unlike the egg-laying reptiles, most mammals give birth to live young and nurture them with milk. This form of parental care, called lactation, meant that the young could be more developed and better protected in their early, vulnerable stages. It was a subtle but profound evolutionary advantage, a quiet innovation that gave mammals an edge over their competitors. And it's also a powerful symbol of our shared mammalian heritage, a biological thread that connects us to every other mammal on the planet. This era also brings us to a beautiful and humbling scientific concept: adaptive radiation. This is the process by which a single species or group of species evolves into many different forms to fill new ecological roles. The mammals after the asteroid impact are the perfect example. The world was like a great empty stage, and the mammals were the new actors, trying on all the different costumes and playing all the different roles. It's a reminder that evolution is not a slow, linear march toward perfection, but a messy, creative, and often chaotic process of exploration. Now, let us consider a strange and curious scientific fact. Among the many branches of the mammalian family tree, a group of quiet, tree-dwelling primates was evolving. They were not particularly strong or fast, but they had a crucial new development: a brain that was growing in size and complexity. This was the beginning of our own story. This was the moment when the power of thought and consciousness began to take center stage. But what exactly is a brain, and how did it give us this incredible ability? The brain, in its essence, is not a simple organ. It's a vast, intricate network of interconnected neurons, a kind of biological theater where thoughts, memories, and emotions play out. It's a structure that allowed our ancestors to do something that no other creature had ever done before: to think abstractly, to plan for the future, and to understand the past. It was an instrument of unimaginable power, and it was still a work in progress. As we look at the rise of the mammals, we are not just looking at the story of how our ancestors came to be. We are looking at the story of how an entire class of animals, from the smallest shrew to the largest whale, inherited a broken world and remade it in their own image. It is a story of quiet resilience, of adaptation, and of the profound beauty of a second chance. The world had been reset, and the stage was now set for the most complex, most self-aware, and most dangerous creature the planet had ever seen. The rise of the mammals was a story of quiet triumph, but within that story was another more specific journey: the evolution of the human brain. For millions of years, our primate ancestors were not the dominant species. They were simply another branch on the great tree of life, living in the canopies and foraging for food. But a change in their environment, a shift in the climate that saw the great forests shrink and the grasslands expand, forced them to do something new. They had to leave the trees and learn to walk on 2 feet. This act of bipedalism, walking upright, was a pivotal moment. It freed up our hands, allowing us to carry things, to use tools, and to manipulate our environment in a way that was previously impossible. But it was the brain that truly set our ancestors apart. Over millions of years, the human brain grew in size and complexity, a rapid and unprecedented growth that no other animal has experienced. This wasn't a linear process. It was a series of fits and starts, driven by a complex interplay of environmental pressures, social needs, and a feedback loop between tool use and brain development. The brain, at its most fundamental level, is a complex network of electrical and chemical signals. It's an information processing machine of unimaginable power, with billions of neurons firing in intricate patterns. It's the organ of consciousness, of memory, of language, and of the ability to think abstractly. You can think of it as a kind of a theater, where different parts of the brain take on different roles. The back of the brain processing visual information, the front of the brain handling logic and planning. But the most interesting part of this theater is not the actors, but the stage itself, the intricate connections that allow for a single, unified experience of the world. And this brings us to one of the most profound and unsolved mysteries of science: consciousness. How does a collection of electrical signals and chemical reactions give rise to the subjective experience of being alive, of seeing the color blue, of feeling love or sadness? We can map the brain, we can watch it light up in an fMRI machine, but we still don't have a clear answer to the hard problem of consciousness. The question of why physical processes should feel like anything at all. It's a question that physicists, neuroscientists, and philosophers are still struggling with. A profound reminder that even in an age of immense scientific progress, the universe still holds its most intimate secrets close. The developing brain of our ancestors allowed for something truly revolutionary: storytelling. We are the only animals that can communicate not just what is happening now, but what happened in the past and what might happen in the future. This ability to weave narratives, to share knowledge and experience across generations, was a powerful evolutionary advantage. It allowed us to learn from the mistakes of our ancestors, to pass on complex ideas about hunting and foraging, and to create a shared culture that bound us together. Remember we talked about the great extinctions and the end of the dinosaurs? The first humans, even in their earliest forms, were storytellers. They were the first to begin making sense of the world, to look up at the stars and wonder where they came from. They were the first to contemplate their place in the grand narrative of life. And this is a beautiful and little-known truth about us as a species. We are not just tool users, but we are also the ultimate storytellers, weaving a great complex narrative about ourselves and our place in the universe. We are the planet's memory, a living record of a journey that began with stardust and fire. With our new brain and our newfound ability to tell stories, our ancestors were ready to embark on a new kind of journey. They were no longer just reacting to their environment. They were beginning to actively shape it. The quiet tribes of our past were about to start a new kind of a migration, a great global trek that would see them colonize every corner of the earth, from the coldest tundras to the hottest deserts. They were ready to leave their home in Africa and spread out across the world, carrying their stories and their secrets with them. The story of our species is a story of movement. For hundreds of thousands of years, our ancestors remained in Africa, a single unified group, evolving and adapting to the changing landscape. But around 70,000 years ago, a small group of them, perhaps as few as a few hundred individuals, embarked on a great journey. They left their ancestral homeland and began to spread across the globe. This was the Great Out-of-Africa Migration, a quiet, steady push that would see humanity colonize every continent on Earth, save for Antarctica. This was not a planned expedition. There were no maps or guides, It was a slow generational process, driven by the search for new resources, a desire to escape environmental changes, and perhaps just a deep human curiosity. They moved along coastlines, following the herds of animals they hunted. They crossed vast open grasslands, and they adapted to every new environment they encountered. This was the birth of human diversity. The different skin tones, hair textures, and facial features that we see today are all a result of our ancestors adapting to the different climates and conditions they encountered on their long journey. Imagine the courage it took. They were not giants or great beasts, but they had a unique kind of strength, their adaptability, and their social nature. They lived in small, tight-knit tribes, sharing knowledge and resources and working together to overcome challenges. Their success was not in their individual power, but in their collective intelligence. This is a subtle but profound truth about our species. We are at our best when we are working together, when we are sharing our knowledge and our stories. One of the most fascinating and little-known scientific facts about this period is the Hobbit, or Homo floresiensis. These were a group of archaic humans that lived on the island of Flores in Indonesia. At the same time, our own ancestors were migrating through the region. They were incredibly small, only about a meter tall, and they had a brain the size of a chimpanzee's, yet they used tools and hunted. They are a powerful reminder that the story of human evolution was not a straight, linear path, but a messy, branching tree, full of different experiments and different ways of being human. And it raises a humbling question. What other branches of our family tree existed that we have yet to discover? This period also saw the development of a powerful new tool, fire. Our ancestors had long known about fire, but they learned to control it. They learned to make it, to keep it burning, and to use it for warmth, for protection from predators, and most importantly, for cooking. Cooking made food easier to digest, which meant our bodies could get more energy from the same amount of food. This surplus energy was crucial. It fueled the growth of our brains, allowing them to become even bigger and more complex. It was a simple technology that had immense consequences, a kind of biological feedback loop that propelled us toward our modern form. The quiet wandering of our ancestors was a kind of a final, great migration. It was a time when humanity was still truly wild, living in harmony with the natural world, in small groups, and with a deep, intimate knowledge of their environment. They had not yet settled down. They were still nomads, still wanderers, still a part of the great, quiet, and ancient rhythm of the planet. But something was about to change. The wandering was about to come to an end, and with it, a new kind of civilization and a new way of being human was about to begin. The stage was set for the next great act, a revolution that would change not just our way of life, but the very relationship between humanity and the earth. The quiet wandering of our ancestors was about to come to a profound end. For millennia, humanity had lived as hunter-gatherers, following the animals they hunted and foraging for plants, a nomadic existence dictated by the seasons and the availability of food. It was a lifestyle that required a deep, intimate knowledge of the natural world, a kind of wisdom passed down from generation to generation. But around 10,000 years ago, in scattered locations across the globe, a new idea took root. Our ancestors began to settle down. This was the agricultural revolution, a pivotal moment in human history. It was not a single sudden event, but a slow, gradual shift that happened independently in places like the Fertile Crescent, China, and the Americas. Instead of hunting and gathering, humans began to domesticate plants and animals. They learned to plant seeds, to breed animals, and to store surplus food. It was a radical departure from the way we had lived for hundreds of thousands of years, and it changed everything. The consequences were immense. With a reliable food source, human populations began to grow. We no longer had to constantly be on the move. we could build permanent homes, and these small settlements slowly grew into villages and then towns. This newfound stability allowed for a new kind of social organization. People could specialize in different tasks. There were farmers, of course, but also toolmakers, potters, and weavers. The concept of surplus food meant that not everyone had to work to find food, and this freed up time and energy for new innovations and cultural developments. This revolution also brought with it a different relationship with the natural world. Instead of simply living within the ecosystem, humans began to actively manipulate it. We cleared forests to make way for fields. We diverted rivers to water our crops, and we altered the very genetic makeup of the plants and animals we domesticated. It was the beginning of our journey to becoming the dominant force on the planet, a journey with both immense benefits and profound costs. There is a fascinating and often debated scientific theory about this time known as the Jared Diamond hypothesis, or more simply, the idea that the agricultural revolution was a catastrophe. While it led to population growth and technological advancement, it also brought new problems. Our diet became less diverse, leading to nutritional deficiencies. Living in close quarters with domesticated animals led to the spread of new diseases, and the concept of land ownership led to conflict and warfare. This raises a philosophical question. Did we trade a life of nomadic freedom and health for a life of settled stability and disease? The truth is, it's not a simple answer, but it's a powerful reminder that every great step forward in our history has come with a price. This period also saw the development of a powerful and crucial concept, the domestication of fire. We've talked about fire before, but now its use was different. Instead of just using it for warmth and cooking, our ancestors learned to use it to reshape their world. They used it to clear land for farming, to create charcoal for smelting metals, and to bake clay into pottery. It was a technological leap that was as important as the revolution in agriculture. It was the moment when fire became not just a tool for survival, but a fundamental tool for civilization. With settled life and a reliable food source, the stage was set for the next great human innovation. The small scattered villages of the world were about to become something more. They were about to become the first cities, great hubs of culture, trade, and learning. And with the rise of the city, a new kind of human story, a story of empires and monuments, of art and science, was about to begin. The quiet revolution of the sower had paved the way for the bustling, complex world of the city dweller. The quiet villages of the agricultural revolution were the seeds of a new kind of human organization. As populations grew and food surpluses became more common, these settlements began to coalesce into something more complex. The city. The first cities, like those in Mesopotamia and the Indus Valley, were not just larger villages. They were centers of trade, culture, and power, and they fundamentally reshaped the human experience. The city was a place of specialization and collaboration on a scale never before seen. The baker no longer had to farm. The weaver no longer had to hunt. This division of labor allowed for an explosion of new skills and technologies. It was in the cities that we find the first true artists, the first engineers, and the first scribes. They were places of immense creativity and innovation, a kind of urban crucible where new ideas could mix and ferment, leading to a profound cultural flowering. But the city also created a new set of challenges. It required a new kind of social structure, one with laws, governments, and a hierarchy to manage the complex needs of a large population. It was the beginning of the state, of the concept of a shared identity that extended beyond the family or the tribe. The city was a new kind of ecosystem, one that was no longer purely natural, but was a human creation, a place where the rhythms of life were dictated not by the sun and the seasons, but by the clock and the calendar. This brings us to one of the most remarkable and underappreciated inventions of this era: writing. Before writing, all knowledge was passed down orally from one person to another. This was a powerful but fragile system, vulnerable to the loss of a single person or the vagaries of memory. But with writing, knowledge could be stored and passed down with perfect fidelity across generations. It was a kind of external brain, a technology that allowed for the accumulation of knowledge on a massive scale. Imagine the profound effect this had on our species. Suddenly, a king in one city could send a message to a king in another. A scribe could record the laws, the history, and the myths of a people. It was the birth of history itself, the moment when our story began to be written down, a silent record of our journey from stardust to civilization. It also raises a philosophical question. Does writing change the way we think? Does it make us more logical, more linear in our thoughts than our oral ancestors? It's a fascinating, unanswerable question. Another interesting and little-known scientific fact about this era is the invention of urban sanitation. The first cities were incredibly dense and unsanitary, leading to the rapid spread of disease. Our ancestors, through trial and error, began to develop crude forms of sanitation, like latrines and sewer systems. This was a crucial step in human health, a quiet but profound innovation that allowed cities to grow to their immense sizes. It was a kind of a silent, urban experiment in public health, a testament to the fact that even in our greatest moments of cultural triumph, we were still grappling with the most basic needs of our bodies. The city was the beginning of a new kind of human journey, a journey from the natural world to a world of our own making. It was a moment of immense creativity and immense peril, and it set the stage for everything that was to come. With the city came the concept of an empire, of a shared identity that transcended the local, and with it, the first organized warfare. It was the birthplace of both the best and the worst of what we are capable of. The story of our species had just entered its most complex and most dangerous chapter. The city, with its new systems of governance, trade, and communication, created a fertile ground for the growth of something intangible but incredibly powerful. Ideas. As people lived and worked together, they began to ask bigger questions. They looked up at the night sky and wondered about the stars. They looked at the world around them and wondered about its fundamental nature. This was the birth of philosophy and science, the first quiet moments of a new kind of human inquiry. The first philosophers, like the pre-Socratics in ancient Greece, were not just speculating. They were trying to find a unifying principle for the universe, a single, elegant idea that could explain everything. Thales, for example, believed that the fundamental substance of all things was water. Anaximander proposed a more abstract concept, the apeiron, an undefined and boundless principle. These early inquiries, though they may seem naive to us now, were the first steps toward a systematic, rational way of understanding the world. They were the first whisperings of a new language, the language of logic and reason. This philosophical inquiry was inextricably linked to the development of science. The ancient Greeks, for example, made remarkable strides in mathematics and astronomy. They were the first to propose that the Earth was a sphere, and they accurately calculated its circumference. They charted the movements of the planets and developed a powerful geometric framework for understanding the cosmos. This was not a purely academic exercise. It was driven by a deep human curiosity, a desire to know our place in the universe, and this brings us to a fascinating and little-known scientific paradox: the epistemological problem of the past. We have a great deal of information about the history of the universe and our planet, from the Big Bang to the present day. But how do we truly know if our models are correct? We cannot travel back in time to observe the formation of the Earth or the extinction of the dinosaurs. We rely on a chain of reasoning and evidence, from the redshift of distant galaxies to the fossil record in ancient rocks. This is a subtle but profound mystery. Our knowledge of the past is not a direct observation, but a beautiful, elegant reconstruction, a kind of a woven tapestry of ideas and evidence. This raises a quiet but persistent question. Are we just telling ourselves a convincing story? Or are we truly grasping the reality of what happened? The truth is, we don't really know. But it is this very mystery that drives us to continue our inquiries. The development of ideas also led to a new kind of human community, the scholarly tradition. For the first time, people could devote their entire lives to the pursuit of knowledge, to the study of the stars, or the classification of plants. This was a radical departure from the life of a hunter or a farmer, and it was a crucial step in the accumulation of human knowledge. It allowed for a kind of an intellectual conversation that spanned not just cities, but centuries. The invention of metallurgy, the ability to extract and work with metals like copper and iron, was another crucial technological leap in this era. This was not just a new tool. It was a new way of thinking about the world, a new way of understanding the properties of matter. It was a kind of a primal chemistry, an understanding that you could transform a dull, unyielding rock into a sharp, beautiful tool or a powerful weapon. This was the beginning of our love affair with technology, the first stirrings of our desire to not just understand the world, but to reshape it with our own hands. The journey of our species had moved from the great physical migration across continents to a quiet, intellectual migration into the world of ideas. We had learned to build cities, to write our stories, and to ask the big questions. And in doing so, we had created a new kind of civilization, a great tapestry woven from countless threads of knowledge, belief, and ingenuity. The stage was now set for the final act of our story, a story that would see us not just understanding our world, but beginning to shape our own destiny. The journey was not over, but it had entered its most curious and most dangerous phase, as we now hold the power to shape not just our own future, but the future of the entire planet. The story of our species is a story of countless threads weaving together into a single complex tapestry. We have seen the raw stardust become a molten planet, the fiery rock become a watery cradle, and the quiet microbes become a bustling, complex civilization. But there is one final great thread to consider, a thread that has only recently begun to be woven: the story of our relationship with the planet itself. For most of our history, humanity lived in a kind of a symbiotic relationship with the Earth. We were a part of the ecosystem, not apart from it. We lived in small tribes. We moved with the seasons, and our impact on the world was minimal. But with the agricultural revolution and the rise of the city, that relationship began to change. We began to see the Earth not as a home, but as a resource to be exploited, a canvas to be reshaped for our own needs. This shift in perspective led to an acceleration of technological progress, and with it, a new kind of power. We learned to harness the energy of fossil fuels, to build machines that could do the work of 1,000 men, and to create materials that had never existed in nature. We built skyscrapers that scraped the clouds and dammed rivers that had been flowing for millennia. We bent the world to our will, and in doing so, we created a new kind of civilization, one that was no longer limited by the quiet, slow rhythms of the natural world. This brings us to one of the most pressing scientific and philosophical questions of our time: the Anthropocene. This is a proposed new geological epoch, a period in which human activity is the dominant force shaping the Earth's climate and environment. From the great layers of plastic in our oceans to the carbon dioxide we've released into the atmosphere, we are leaving a permanent mark on the geological record. We are, in a very real sense, the authors of our own geology. The idea of the Anthropocene is a humbling one. It reminds us that we are not just observers of the planet's story. We are active participants, and our actions have global and potentially irreversible consequences. It raises a question: do we have the wisdom to wield this immense power responsibly? Can we learn to live not just on the planet, but with it, in a way that is both sustainable and just? The truth is, we don't know. But it is the question that defines our time. One of the most fascinating and hopeful scientific concepts in this era is biomimicry. This is the idea of looking to nature for solutions to our technological problems. For millions of years, evolution has been a kind of a grand research and development laboratory, and it has produced some of the most elegant and efficient designs imaginable. Scientists are now studying everything from the structure of a bird's feather to the surface of a gecko's foot to create new technologies, new materials, and new ways of living that are more in harmony with the natural world. It is a kind of a quiet, intellectual return to the wisdom of our ancestors, a humbling admission that for all our brilliance, the natural world still holds the key to so many of our problems. The story of our species is a story of a journey that has taken us from the quiet grasslands of Africa to the bustling, interconnected world we inhabit today. We have faced great challenges and achieved incredible triumphs. But now, as we reach the end of our story, a new kind of a journey begins. A journey not across the landscape of a planet, but into the very heart of what it means to be human in a world we have fundamentally and forever changed. The final act of our story is not written in stone, but is being written in our actions, in our decisions, and in our hearts every single day. The sun is setting on our journey, and we have one final quiet question to ask ourselves. What do we do next? We have traveled a very long way, my friends. We have witnessed the birth of a world, the quiet revolution of life, and the strange intellectual journey of our own species. We have stood on a molten rock and looked up at the first stars. We have floated in a primordial ocean and felt the first stirrings of life. We have walked with the great dinosaurs, and we have lived in the shadows of their passing. And we have, in our own time, begun to understand this story, to tell it to each other, and to wonder at the profound journey that has led us here. This final part of our story is not about the past, but about the present. It is about the world we inhabit right now at this very moment. Look around you, wherever you are. Every atom in your body was forged in the heart of an ancient star. The iron in your blood, the carbon in your bones, the oxygen you breathe. It all came from the cosmos, from a time long before our planet even existed. You are, in the most literal sense, made of stardust. You are a living, breathing piece of the universe, a tiny, self-aware pocket of cosmic memory. This is a scientific fact, and it is a poetic truth. And what about the future? The truth is, we don't know. Our story is still being written. But we do know that our planet is a single, interconnected system, a fragile and beautiful blue marble hurtling through the infinite blackness. We are all a part of it, and we all have a role to play in its future. We have the power to create, to innovate, and to build. But we also have the power to destroy, to consume, and to break. The choice is ours, and it is a choice that is being made in every action, every decision, and every thought we have. This brings us to a beautiful and often overlooked scientific concept: emergence. This is the idea that complex systems and patterns can arise from the interaction of many simple parts. A single neuron is just an electrical switch, but a billion of them working together can create a consciousness. A single raindrop is just a drop of water, but a billion of them can create a hurricane. In the same way, we are all just a tiny part of a great global system. But our collective actions, our collective choices, have the power to create a future of immense beauty or immense peril. It is a powerful and humbling thought, the idea that the grand, sweeping story of our planet is being written by the countless, tiny actions of each and every one of us. Another little-known fact that encapsulates this final part of our journey is the overview effect. This is a cognitive shift reported by astronauts who view the Earth from space. They often describe a profound sense of awe, a feeling of interconnectedness, and a deep understanding of the fragility and unity of our planet. They see the Earth not as a collection of countries or continents, but as a single, living organism, a place without borders or divisions. This is a lesson we can all learn from. We do not need to travel to space to see the Earth as a single home. We just need to open our eyes and our hearts, and to remember that we are all, in the end, in this together. And so our long journey comes to a quiet end. We have traveled through time, from the cosmic void to the moment we inhabit now. We have seen a world born, a world remade, and a world that is still becoming. And we have, in a very real sense, come home. The journey is over for now, my friend. Our long path has brought us back to this very room, this very chair, this very quiet moment in time. The whispers of stardust have settled, and the echoes of ancient giants have faded into the silence. You are here, and you are safe. The long, winding river of history has flowed past, gently brushing against you, and leaving you in this peaceful harbor. The fire and the fury of creation, the slow march of continents, the wildness of the first animals, all of it has led to this quiet, simple moment. I'd like to gently ask one last time, where is the place you're staying now? The time in that place, at this very moment, how is it flowing? I want you to feel the comfort of that place, the soft embrace of the space you occupy. And I want you to know that you are a part of this great story, a single, unique note in a cosmic symphony that has been playing for billions of years. Before you drift off, take a deep, slow breath and let go of the day, of the worries, of the sounds of the world around you. Let the long journey we have taken together become a part of your own peaceful dream. If you enjoyed this journey, perhaps you will join me again for another story, another time. Sleep well, my companion. Wherever and whenever you are, sweet dreams.